Hello everybody, can everybody hear me first of all? Good. What I'm going to really be talking about today is how the innovations and innovative technology that Proceq have produced over the last couple of years have changed how my company and we apply this technology to some particular types of testing. So initially, the first part of the talk will be about post-tension special inspections. We predominantly do these on bridges in the UK, but we've actually done work on structures such as car parks and buildings. With respect to the highway side of things, the Department of Transport a number of years ago set up a couple of papers that were guidance notes for engineers in the UK. The reason was there'd been a number of failures of post-tension bridges across the planet. One which really made the DTP have a knee-jerk reaction was a bridge fell down in South Wales in the UK with no apparent signs of warning. From that, there was a moratorium put on PTSI construction and a massive bridge testing programme, which is now being looked at again. And in the because of what's happened very recently in Italy with the Marina Bay Bridge falling down, and obviously massive loss of life for over 50 people, people are now really looking to make sure that when we look at post-tension structures, we are looking to find the hidden defects that have caused some of these major problems. Now, the problem that we had a number of years ago when we first started this in the late 1980s is the technologies were very limited. One, to even detect where the tendons were. And being as you can see on this photograph, the tendons in bridges do not run straight. They're always profiled because of the load-bearing reasons that they're there. So the first problem was how to find them. Secondly, we then had to try and attempt to determine which areas of these tendons were at high risk of corrosion. And generally, they're at high risk of corrosion where there was a lack of grout within the tendon. This is something that up until very recently, the only technique that you could do that had any chance of picking up these voids was X-ray. X-ray is very expensive, and to actually, if one of the structures in the middle of Singapore was post-tension, you cannot evacuate a massive area around the bridge, and this is what you have to do with X-rays. So, because of that, there's lots of publications by the Department of Transport back in the UK to say, well, these are the areas we think you might have to have a look at. But generally, it was very much we'll just have a look in there, at the areas of most at risk. But it wasn't very scientific. Now, this is a structure we looked at in Southern Ireland, where the client there, the National Roads Authority, were very concerned. It was a recently constructed bridge, and the cracking that you can see that we've highlighted here with the red were directly underneath all the tendons in the bridge deck. They were concerned that these may have been induced because of corrosion in the tendons, so we had to do some work on there. Now, in that first instance, it was quite easy to see where they were because the cracking was directly under the tendons. But what tends to happen is we don't know where the tendons are. And using conventional cover meters, you tend to find that you're going to have a problem in picking anything up behind that front mesh of steel. This is a couple of photographs here where you can see inside the tendons. And I think some of these were used yesterday. So what we have here is, this is a wire that has actually no grout surrounding it at all. If you get water into the duct, and because certainly in the UK and in a number of other countries like the US, we pour thousands of tons of salt on the road every day during the winter months when it's snowing. Now, as everybody knows, salt and concrete, which has got embedded steel, are really not very good bedfellows and will cause corrosion. Here we have a photograph of a tendon which is partially voided. Now, on this one, we're very lucky that the wires within the tendon duct are actually within the ground. So, although there is a void, the actual risk to corrosion is far less. Now, we have a little video to look at, and this is one of the structures in London, which is one of the major arteries into London. And this is what the tendon looked like when we put a borescope in there. As you can see, one, there's no grout. The wires here, you can see there's got a lot of surface corrosion, and in some instances, they're completely snapped through. This structure was constructed very similar to the one in Genoa. This one would have fallen down as the one in Genoa did, had we not in the UK decided to externally post-tension this. So the existing post-tensioning was just redundant, and we put a completely new system on to keep the bridge up. So originally, a number of years ago when I first started doing this, as I said, we had drawings like this that we had to trawl through to see where the tendons were. And as you can see on the top one, not very clear, you can see that the tendons are draped down so that they're at the mid-span area, at the low point of the span. We used this, and then we had to use a cover meter to try and determine the steel in the area that we were going to be drilling into the tendon. If we were lucky, we would actually get some drawings like this, which actually show a far clearer demonstration of the as-built drawings. These are the lucky ones. We've actually got drawings. There's a number of bridges in the UK, we have no drawings, and I'm sure that's applicable across the planet. So this would be how we used to do it originally. We run a cover meter across here, and what you can see is, and what would actually really happen is, we would pick up these bars, but you'd probably never pick up the tendons behind because of the limitations of electromagnetic cover meters. So how did we actually find where the tendons were? A costly and timely stitch drilling approach. I think if you ask any owner of a bridge, are you happy we just drill loads of holes in your bridge just to try and find out where the tendons are? They're not going to be very happy about it. And this is a classic of what you get. So as you can see here on the panel on the right, we've had to do a cover meter survey to pick up the steel, and then we've had to attempt to drill to locate the tendon. Each one of these drills could be quite deep, take a long time, and damage the bridge. Now, as you can see, once we did locate it, we then overcored to actually allow us to get into the tendon to investigate what was going on inside. But again, this is just a selected area. We haven't chosen this for any real reason apart from the bridge engineers said this is a high-risk area. And as you can see, the photograph on the left, you can see the drill holes coming down where we've just touched the sheath. So this is an expanded aluminium sheath, which is generally what we find in bridges in the UK. What we're tending to find, and I think it will probably be applicable elsewhere in the world, is highway structures. We get most of the work that's got to be done at night when we can close the motorway or bridge. However, a lot of the work and a lot of the bridges, certainly in the UK, there's a real concern about is rail bridges. Now, on rail bridges, we'll have, in some instances, only maybe an hour and a half to 2 hours on the structure. Now, if I have to go along there with a drill and take that many drillings, I'm not going to get many done. So there's a real cost implication to it, and within that, we're going to be looking at less areas on the bridge, which gives us less coverage. So, we've all heard from Isaac and other guys from Proceq. Proceq decided to bring in the GPR Live, which we have and we use. Now, the great thing about the GPR Live is it will pick up tendons at depth. There are limitations, and there are certain companies out there that will just say their radar works all the time. I'm a little bit more realistic and not non-economical with the truth. So what you will find is in certain areas where you do get, and as has been mentioned before, a very high concentration of steel, whereby the actual window of concrete you're trying to look through, look to something behind it, can be limited. It can sometimes limit the amount of information you get. So now, using the new technique, we can go along and find every tendon first time. And I'd say 99% of the time we're doing this, this is what happens. This is actually real data off a job that we did very recently on one of the major motorways around the M25, around London. Now, we do have and use other competitors' radar sets, purely because GPR only came about, the GPR Live only came about 2 or 3 years ago. However, on this bridge, they were useless. They couldn't determine the deep tendons that we were looking at. So what you've got here is, so what we've got here is, this is a rebar, this is a rebar, this is a rebar. As you can see, they're around about 70 to 80 mil deep. So the reinforcement is actually quite deep on this bridge. This was a 2 metre wide parapet, which was massively highly reinforced. These are the 3 tendons that we've had to look at and investigate. As you can see, these were down around about 270 mil. What we normally do is we normally carry out, once we've investigated where the tendon is and how to break into it, we normally put 100 to 75 mil core barrel right the way down, so we can actually expose the entire circumference of the tendon to get a really good idea of what's going on. Here, because of the limitation of the steel, we couldn't do that. It was virtually less than 50 mil. So, as far as I know, there's no other bit of kit that could have done this for us on this job. So this is a classic example of what we've got. On the right-hand side, the white chalk marks are the profiles of the tendon as determined by GPR, and the reinforcement pattern, again, as determined by GPR. So you can see that we've been able to hit the 3 tendons with 1 drill hole and then overcore it. So very quick technique, we're getting lots of information. However, we're just willy-nilly drilling holes in bridges. What has been a major concern, and there was an article, a TV programme very recently in the UK about the bridge that fell down in Italy and in Genoa, that the cable stays were actually post-tension. They'd actually done some work a couple of years ago where they'd found where there was voids, they had got water into the tendons, causing corrosion. At this point, they decided, very similar to the Hammersmith flyover, which I showed you the video of earlier, they decided to externally post-tension these cable ducts. They did 2 or 3, why didn't they do and look at the others? They decided, I think there was a lot of politics flying about, but they basically didn't look at these other structures. And what they needed to do is ensure that they could pick up the voidage. Now, the bit of kit that's being talked about a lot today can do that. This was probably over 2 years ago. We were doing a large investigation on a complex junction in London near a very large shopping centre, and it was just the last day working on there. We found, as you can see here, this is the duct, so you've got this is the extruded aluminium sheath, which we've broken out, and you can quite clearly see one of the pre-stressing strands in there. This grey material is the ground, it should be protecting it. And as you can see up here, we have a nice big void. At that time, my engineer on site spoke to me and said, what do we do? So here is where we actually had this, and down at this location here, we did another one just down slope on the tendon and did an exactly identical investigation. Here we found a void, here we found it was fully grouted. So at this point, knowing that Proceq and producing this equipment that we can potentially use and try and get some feedback from it, we got them to come out and do some scans. So this was the readings that were done directly above this area. The void was probably easily half a metre either side of where we'd broken out. So as you can see, we've got 4 scans with the Pundit Live array showing really good targets. We then went onto the second one. And as you can see from the photograph down here, fully grouted. Yeah, that's what we'd like to see every time. And as you can see, the response coming back from the Impulse Pundit Live array was completely different and indicating that it was fully grouted. This is just an indication of what we give our clients at the end of the day. So what you have here is These are photographs down core holes or breakouts, exposing the wires, fully grouted, everything's happy. What we do as a company, and we push this with the Department of Transport in the UK, is it costs us a lot of money to get into these areas, so we might as well do some other concrete testing. So here is a condition survey panel that we do, which determines depth of cover of the reinforcement, half cell potential, gives you a potential of corrosion, and dust drillings to see if there's any chloride, which gives me, as an engineer, a far better handle on being able to do an interpretive report for you. If anybody was here last night, you would have seen these photographs. These are actual photographs from all the jobs that we've recently done. And the two where we say it's high risk and medium risk are from this particular job. Now, that's not what you really want out of your post-tension duct. This was a car park that was less than 5 years old. All I can say is it's in a very cold country, very near England. And what happened is they pulled the tendons through the ducts in the winter. These ducts, there was a problem in the construction where the ducts filled with water, froze. When they came to grout them up, because of the frozen ice in the duct, there wasn't any grout injected into it. It was very sort of like haphazard. And yeah, not a really very good example of how to post-tension structures. This is another example, again, with respect to post-tension investigations. We had an inquiry from a client up in Scotland who had some beams that they knew that they'd had problems with grouting during construction phase. So they asked us to come along, and as you can see up, as you can see up here, this is the tendon. So these are each scanned, and as you can see, we get this lovely great target that we're looking for the air gap. These down here was the back wall because it's quite a narrow I-beam. They asked us to scan a number of the beams to determine exactly the condition of them, and then use the pundit live array as a QC check once they've actually grouted them up. So as you can see here, this is the scan after grouting, which, as you can see, even if you're not in it, my wife even can determine what's good and what's bad on this, so it's a very easy technique. And this is a classic. You can see the pink chalk mark, which is the tendon profile, which has been determined by radar. And these are actual live scans that are being carried out on the tendon. Vitally important, we know where the tendon is. Years ago, we did some work where impact echo was all de rigueur, and we were doing works on it, and they hadn't even, the firm who done this work hadn't even done the impact testing above the tendon, which means it's very critical. Now, people are going to say, what else can you use it for? Obviously, I've been extensively talking about post-tension ducts and how that was where we first got involved with it. However, because we've got the equipment and because people come to us and say, we've got this problem, what can you do? We had a situation where some years ago, probably 7 or 8 years ago, I tested a bridge very near my office, and more latterly, someone had come in and done some repairs. The top of the bridge had got highly contaminated with chloride. The consultant at the time just said, right, we'll strip all the contaminated concrete back well behind the reinforcement. It was a very highly reinforced abutment on a bridge. They then sprayed on a shotcrete or gunite type repair, and there were some problems with some rundown from the top of the abutment which washed some of the repair away. And on washing the repair away showed that you had large areas of voidage. The client was jumping up and down going, this isn't the job I paid for, how can we determine where the voidage is and what's the extent of the voidage? They got a firm in who thought GPR was the way forward. It can work given the right conditions, but because of what's been explained before, I won't go too much into it, well, I probably will. You need to think about utilising, in some instances, more than one technique to actually get to your end goal. So what we have here, these are some scans that we found these targets, which we perceived to be voidage. We then, and unfortunately with a lot of the NDT that we get involved with, people won't take my word for it. Oh, this is all new warrant. You know, although we've been using it for 2 years, they still, because it's not out there in the ether with respect to the UK business, we still have to do some calibration. And unfortunately, it does mean we get down and do some dirty coring work, which we don't particularly like to do. But what you can see on the right hand, this is the core hole. So you can see this area here is the shotcrete repair, and you can see the more buff coloured concrete at the back end of the core hole is the parent concrete. And what they were finding is, and this is classic, this is your rebar. We've had to actually cut one of the rebars because they were very tightly spaced. So this is a 50mm diameter core, and we've just had to pinch that rebar. But what you can see here is a lovely void, which is to me is lovely, but not to the client. You can see in this middle picture, this is us again doing one of the areas which this had come about because of this exposure here. So you can see a really close spacing to rebar. Trying to get a 50mm core through was difficult. A previous testing house used radar and said it doesn't work. And I think this is the first core hole we did, and we thought, there's the steel. Yeah, this technique doesn't work, does it? No, there's no void here, it's fine, as you can see. On this bridge, we carried out 6 test panels, of which 4 were positioned above areas where we got really strong targets. 2 were above areas where we thought were fine. And we haven't got photographs of the cores, but the cores all show a degree of honeycombing where we picked up the voidage, and the 2 areas we thought were very good came back with fully compacted repair. So it's really belt and braces for us. People ask me, what application can you use GPR? Well, you've seen us do a few here with picking up post-tension ducts, a glorified cover meter. What is great, as we explained, here we have multiple layers of rebar, and we've got a back wall. What it can make you do is it can reduce the amount of intrusive investigation work you need to do. We do a lot of slab investigations where people want to know what's the condition of the slab, the thickness, ground bearing conditions beneath, and ostensibly, as Dave mentioned about pundit work, take loads of cores, and then we know exactly where the slab changes its thickness. You don't need to do that anymore. What you do a scan like this, core at this location, and this is reading, and I'm just making up here, 21.1 centimetres. Once you've got your actual core out, you measure it, and then you can put down the actual depth of the slab. That then calibrates the GPR live. You can then run this across the slab to your heart's content. Where you get variations, it will be thicker or shallower. It will save you coring. Now, why have we got a GPR live sitting on the top of a whiskey barrel? We just happened to do a lot of work for a company who manufacture whiskey in Scotland, and I did actually think they were pulling my leg when they said, we need to know how much evaporation of the whiskey has occurred. Also known as the angel share, which is a Scottish term for it. We used a number of radar sets, one of which was the GPR Live, and where you can see where we've marked on there, that's whiskey below, I wouldn't say fresh air, but an air gap above. So when anybody asks me, what can radar be applied to? Concrete to whiskey, and whatever's in between, really. This one on the left-hand side is using, well, we had to use another system because the Proceq system is limited to the depth that it's got. Obviously, having heard what's happening and what's being released very shortly, this type of survey, this is a culvert that was buried under a road. So that's the sort of survey we'll now be able to do with GPR from Proceq. Again, just another, these were some, a lot of the times I said we need to calibrate, these were some jack arches. So what we're actually finding here, we thought these might have been jack arches. Actually, these readings here with the beams in here. You had an I-beam that was supporting the jack arch. So again, there's information the client didn't even know the structure was there in the first place. This is a slab near the sea up in Scotland. The tide's coming in and water's coming through a drill hole that we put in there. What's happened is the fill material beneath this slab has been completely washed away. And again, this was a project that we were able to use the pundit to determine the voidage under a slab. You've probably seen this a number of times from a number of the guys at Proceq, so I won't go through too much about the technology because we know what's going on. Effectively, this was a slab we were asked to look at and investigate up in north of England. It was a fibre reinforced slab which also had some conventional reinforcement in it. They had gone to start to drill in some anchors for a racking system for a major electrical supplier in the UK, and they drilled into some big voids, not voidage, we mean big voids. They again had got a so-called expert in to have a look at the slabs to work out the extent of these voids. They used ground penetrating radar. As we've been shown, 95 to 96% of the radio wave coming out of a GPR set will be reflected by metal. So it was just a complete mismatch of readings. No one could pick, well, they couldn't even pick up the reinforcement in the slab. So we actually said, no, we think you're using the wrong technique. Let us have a go at it with the pundit. So as we can see, some of the pundit will go through steel. So I think it's, again, I'll be corrected. I think about 40% of the ultrasonic pulse will be reflected back from steel, but meaning another 60% will go through the steel. So where we have an air gap, we'll be able to pick it up. And this is exactly the explanation of what's happening here. But we've seen all this. Let's see some real stuff that we actually found. So, originally, having spoken to Dave about detecting voids in tendon ducts, I spoke to Dave when we came over and did some training at the office in Zurich. With respect to voids in tendons, can we get an indication of the amount of voidage, i.e. if it's just half the duct voided or the whole duct? Basically, it's going to come off of an air gap. We can't really determine the amount of voidage present. So again, we knew there was a limitation when we applied it to post-tension structures. However, what happened on this structure, and as I say, we had 2 teams working 12-hour days and 2 teams working 12-hour nights for about 6 weeks. This slab was 80 metres by 80 metres. We've probably got more information coming off of this than anywhere else. And what we found is good quality concrete, which we've got here. So we've got 3 scans, and what you can see is a very, very clear back wall echo, around about 300 mil deep. What we found, let's go to the worst case scenario, significantly voided. We mean there was like a 100 mil gap for a very large extent. What happened there is there was no back wall echo. This is what we were getting. And what we've found now, with looking at the data and having calibrated this with some cores that we had to take and some other work that the contractor did, here we were getting a partial back wall echo, but we were getting targets. And this area here is what we would call isolated voids. So, good quality concrete, that's the scans. We're now looking at the A scan here, so you can see very little scatter along here, and a nice big peak where we're getting change in material type. That was taken out of an area that we had designated clear and good quality. Again, we're now going to the isolated voidage. When you start to actually have a look at the A scan, you can see there's far more scatter on here. You're still getting a nice scatter right at the end for the back wall echo. And this is typically the voids that we found. So you can quite clearly see these are the metal fibres in the concrete, and that's your rebar. And there's another rebar there. Okay, this is the one where we have a big void. Now, they weren't very happy with that slab. I think you can see why. And these weren't isolated, these were all over the slab, hence why it took us, I'd hate to think how many actual scans we've taken here. These were some cores that were taken initially by the contractor on site to actually ascertain what was the problem. Now these are just a couple of examples of what we at Henderson Thomas have used the Pundit live array for. No doubt we will find more applications like we've done with the radar. I love these photographs. I just think this is why, you know, when it all works, probably not very nice for the client because he's thinking, you know, how the hell do I deal with this? But strangely enough, we've been called back now, and what they're doing is they're actually resin injecting these gaps, and they're then getting us to use the Pundit live array to check that it is fully grouted up again, so they can then utilise the slab. Thanks very much. I think if there are any questions, but like I say, we've been using this Pundit for the last couple of years. My experience with Pundit goes back probably 30 years. The company that Proceq bought out a few years ago actually did the original Pundit, which did have limitations because it was great if you could get to both sides of the concrete. This really takes us into another scope of works. And I don't know what the applications will be, but there are two that I'm sure you will face all around the world. Thank you for listening to me.